Hello, thanks so much for joining me today. We're talking about a problem that joins kinematics and forces together. So let's go ahead and see how this problem can be approached. We are talking about you doing three things here. So there's three parts to your trip. You start off by being on roller skates and pushing a box. So there's you pushing. So there's a force acting on you, which is the box pushing back on you. You are moving forward. You move a certain distance, 0.7 meters. Then you skate at a specific velocity, constant velocity, and that's without a box. So that's when you just you stop pushing the box, and you're just basically skating with no box to push, and then you start slowing down. And you're pushing on the brake now on your roller skates, and then you're causing a force in the opposite direction, which will actually slow you down until you stop. So a couple of typos here, you're slowing down. And then of course, this here, you are pushing on the box. Just after you stop pushing on a box is the second part of the trip, and then you start to slow down. So if I'm to draw a velocity time graph here, you start at zero velocity, you're starting at rest, and then you're starting and you're pushing on this box. Your velocity final will in fact become the initial velocity of the second part of the trip. The second part of the trip is you just going at a constant velocity, no box anymore, you're just coasting. And then the third part of the trip, so the final velocity on the second part becomes the initial velocity of your third part of the trip, and that third part of the trip includes you slowing down until you get to a complete stop, and that is your final velocity here, which is zero. So you start off with an initial velocity of zero, you work up to a certain velocity here. Second part of the trip, that velocity stays, does not change because it's constant. And then the third part of the trip, whatever the velocity was, it starts to decrease until it gets to zero. So that's kind of your three parts of the trip. So here you're pushing on the box, you're not pushing, you're just coasting for the second part of the trip here. No push, just coast. And then the third part of the trip is slowing down. So you're actually wanting to come down to a stop. So the first part of the question is really talking about acceleration. And it's asking us to find it during the three parts of the trip. The first part is when you're pushing on the box. So the first thing that you should do when you always do these type of problems is draw a free body diagram. And here's you pushing on the box. I mean, there's the gravitational force here acting on you. There's the normal force because you're a surface acting on you. They cancel each other out because there's no net movement in the y direction. But there is this force of the box applying on you of 130 newtons in the east direction, right? So there's that force there. So if we wanted to find your acceleration, we can focus on your net force in the x direction because that's where the acceleration is happening. We'll use Newton's second law. F net is equal to mass times acceleration. So the net force is really 130. Your mass is 54 kilograms. So from here, it's really easy to find your acceleration, and it's 2.407 meters per second squared. During the second part of the trip, you're at a constant velocity. Now, velocity, change in velocity is acceleration. But if your velocity is constant, it means it's not changing. It's staying the same, whatever it is. So your acceleration is actually zero. So you do not need to calculate anything for the second part of the trip while you're pushing on the box. Now, when you start slowing down, you do need to consider a net force acting on you. So when you start slowing down, again, we've got the force due to gravity and normal force acting on you. And these forces are canceling out because you're not moving in the y direction. However, in the x direction, there is a force, and that is 38 newtons that you're applying to slow you down, right? So that's a force that's being applied in the opposite direction to bring you to a stop. So again, we can use our Newton's second law, figure out what that overall acceleration is, and we'll just apply a negative 38 only because we called the 130 newtons positive here, so this one here is now negative, and we're going to figure out that the acceleration is negative 0.704 meters per second squared, and that will allow us to come to a full stop. So that's fantastic. So there we go, we figured it all out. Now the next part of this problem is now you have to figure out the total distance that you traveled. So you want to figure out the total distance in these three parts of the trip. So when you are pushing on a box, just after you stop, so when you stop pushing on a box, so I don't want to say just after, just when you're when you're not pushing. So maybe here's in the part 2 of the trip. So we'll change this to part 2 of the trip. Not pushing. You're not pushing on a box at all. You're just coasting at a constant velocity. And then part 3 is when you start to slow down. So that's really when you're slowing down and then you come down to 0. So there's 0 velocity, of course, because you're stopping. So during the first part of the trip, when you're pushing on the box, you're traveling at 0.704 meters, and that's your distance. So you're given that. So no calculations needed for the first part of the trip. For the second part of the trip, you do need to figure out what your total distance traveled is. Now remember when I drew the velocity time graph, we said that there's 3 parts of this trip: when you're pushing, and then the final velocity when you stop pushing on the box becomes the initial velocity for the second part of the trip, and that is when you're just coasting. So in order for us to actually figure out this velocity during the second part of the trip, we can in fact try to figure out the velocity final during the first part of the trip. And why would I want to do that? Well, I already just figured out the acceleration, right? I know the acceleration here. I know the initial velocity because we started at 0. So I know a ton of things. I figured out the acceleration on the previous slide. I know the initial velocity, and I know the distance that I traveled. I'm told the distance that I traveled, 0.704, right? For the second part of the trip, the only really thing that I know is that my acceleration is 0, right? Because it's a constant velocity. And I also know my time is 4 seconds during this second part of the trip. That's really all I know. So I don't have my third parameter that I know in order to figure out the fourth parameter, which is the distance traveled. So let's use the first part of the trip here. And we've got so much information about the first part of the trip. So let me go ahead and do that. So we know that during the second part of the trip, we are traveling a constant velocity. Acceleration is 0, time is 4 seconds, but we can calculate velocity for part 1. So there we go. For part 1 of the trip, initial velocity is 0. The displacement or distance traveled is 0.4. Acceleration is 2.4, so we can find out the final velocity. Final velocity formula here that does not involve time is this, and we can really plug in the numbers: 0 and acceleration from the previous problem, and 0.704, which is the distance traveled. We can figure out the velocity final, and that is the final velocity of the first part of the trip, right? So that's the final velocity of this first part of the trip, which happens to be equal to the initial velocity of the second part of the trip. So that's fantastic. Now I got that. So now we can use that to calculate the displacement for the part 2 of the course, because now we have more info. We know during the part 2 of the trip, we know the velocity doesn't change, it stays the same, and it's whatever it was at the final velocity, which we just calculated. The time is 4 seconds, we know that. We also know the acceleration is 0. So we've got those things. We can figure out our displacement, that's really what we're looking for, and it's velocity times time minus 1/2 at squared. The acceleration is 0, so this kind of simplifies the equation into velocity times time, and that's nothing more than 1.84 times 4. So that's how much distance I've traveled during the second part of the course. Now the third part of this course, when you start to slow down, again, the initial velocity is what we can continue to use, because that velocity actually, again, using my velocity time graph, the velocity for the first part of the trip, that's part 1 of the trip, when we're pushing on the box, the velocity, part 1, the velocity final here was what we figured out to be 1.84. Now it's actually not going to change at all for the second part of the trip, and then this here, the part 2 of the trip, when I'm not pushing on the box anymore. And then here's my part 3 of the trip, right? Part 3 here. Mixed up Roman numerals and regular letters. Okay, so part 3 of the trip is here. So what I'm starting off with, my initial velocity here is actually the exact same as the final velocity from the previous part of the trip. So I can say that is 1.84. The final velocity, I'm going to be at a stop, it's 0. Acceleration, we figured it out to be negative 0.704. And that gives me more than enough information to find the distance traveled. By plugging in all the values, I can solve for it to be 1.981 meters. And now to find the total part of the trip, I can just add up those 3 pieces together, and that ends up being 10.1 meters in total that I've traveled. Hope you enjoyed the video. Thanks.